if you can find yours.
So I send these things on to Steve Miller. And it's already progressed there. So I just sent him a message and I copied you on it.
Okay. Yeah.
So you can tell him directly where.
Yeah, that'd be easier. Yeah, so I'm just throwing that video line. Just to clarify, I didn't say that.
If you caught me an hour ago, I hadn't done it yet.
Yeah.
The right thing. You can't know. Okay. And I have sent something to IT Media Services asking them to know.
Yeah, good. All right. Hopefully people can see my screen. Yep, here it works. So, all right. So yeah, I'll be talking about matchable numbers, and this is joint work with Carl Pomerantz, who gave a talk earlier in this conference and kind of gave a nice introduction to a lot of the things that I'll be talking about. So I won't go quite as far into the history as he did. He gave a nice introduction to a lot of the previous work that he's done, but we're mostly going to talk about coprime matchings here. So a coprime matching between two finite sets of integers is just a matching where when you match up two integers, they don't have any prime factors in common. So you have to make sure that you don't pair up any numbers that share a prime factor. So here's a really simple example. Take the numbers 1, 2, 3, 4, and 5, 6, 7, 8. So you can pair 1 with 6, and 2 with 7, and 3 with 8, and 4 with 5. Everything's coprime. And as Carl discussed, there was a Erdős problem involved here, and him and Selfridge ended up completely resolving the question. They showed that there's always a coprime matching between the first n integers and any other interval of length n. So this isn't true for arbitrary intervals, but as long as one of your intervals is the initial interval 1 to n, you can always find a coprime matching between these intervals. And then there's been lots of other work on other sets, and that's sort of where this talk starts, is a setting that comes from a Math Overflow post. So Rechamon in 2022 asked about the set where we take, for an integer n, we'll take d of n to be the set of all its divisors, and then denote by tau of n the size of this set. And we're going to call an integer matchable if we can match up its divisors with the first tau of n integers. So rather than matching the interval 1 to n with some other interval, we're going to match it with the set of some integer's divisors where that integer has that many divisors. So here's an example. We can take the divisors of 6 are 1, 2, 3, and 6. So it has 4 divisors. So we need to match those 4 divisors with the interval 1 through 4. And that's pretty easy to do. You just pair 1 with 6 and 2 with 3, 3 with 2, and 4 with 1. So we find that 6 is in fact a matchable integer. All right, here's a slightly more complicated example. Let's take the number 54, 2 times 3 cubed. So here, in this case, the divisors are 1, 2, 3, 6, 9, 18, 27, and 54. There's 8 of them. So we need to try and pair them up with the interval 1 through 8. And the first thing you notice is that if you look at these divisors, there's lots of things divisible by 3 there. So 3 is kind of going to be our limiting factor. Everything's divisible by 3 except for the numbers 1 and 2. And if you look at the interval 1 through 8, well, we just squeak by because there's 2 numbers that are divisible by 3. So we're sort of forced. We have to match 1 and 2 with 3 and 6. It doesn't matter which one. We can pair them up. We have to match 1 to 6 and 2 to 3. Because if we match the 2 to the 6, then we'd have some problems with 2. But we can get by with the powers of 3. So now we're left with 6 things left over that aren't divisible by 3 in this interval, and 6 things that are divisible by 3 among the divisors. But we still have to be a little bit careful because there's the even numbers to care about. So we look at the even numbers. Well, now we have to pair up the odd divisors here, namely 3, 9, and 27, with the remaining even numbers here to make sure that we don't accidentally pair an even number with an even number. So 3 and 2, 9 and 4, 27 and 8. And now we're home free because we can pair up 6 with 1, 18 with 5, and 54 with 7, and everything works out here as well. So 54 is also a matchable integer. All right, so the first example of a non-matchable number is 8. So in this case, if we were to try to find a bijection, we need to biject 1, 2, 3, 4 with the divisors of 8, which are 1, 2, 4, and 8. And here we just run into troubles with the even numbers because we've got 3 even divisors, 2, 4, and 8. We've got to match those up with these numbers, but there's only 2 odd numbers we can pair those even divisors with. So there's just too many even numbers. We can't do it. We can't pair 2, 4, and 8 with only 1 and 3. So 8 is not matchable. 4 obviously is matchable. If 8's, I just claimed that 8 is the smallest one. So you can match up 4, 1, 2, and 4. Matches with 1, 2, 3. By 1 goes to 4, 2 goes to 1, and 3 goes to 2. But in general, it turns out that if you take any integer divisible by 4, except for 4 itself, that number is not going to be matchable. And the reason for this is just if you look at the divisors in general, 2 tau of u over 3 of those divisors, at least that many are going to be even. So you just look at how many of the numbers have to be even, and the fact that you're divisible by 4 gives you that at least this proportion are even. But if you count how many integers in this interval are odd, well, there's at most this many. And so once your number has enough divisors, that's just not going to work out. So 4 is kind of the last number divisible by 4 that is matchable. And there's sort of a more general principle lurking under the surface here. So yeah, as I said, every multiple of 4 other than 4 is not a matchable number. So in general, we can look at this, and what we find is that if we've got any prime p, and p to the p divides u, well then we're almost out of luck for being matchable. There's just sort of some borderline cases. So if p to the p divides u, and the number of divisors of u is larger than p squared, then u is not a matchable number. So the idea is sort of what we just saw for 4. So if p to the p divides u, then at most tau of u divided by p plus 1 divisors are co-prime to p, but we can count how many elements of this set are divisible by p, and as long as we've satisfied this hypothesis, that's enough to force that there's just too many multiples of p in this set to possibly match everything up. Okay, so sort of these p to the p is sort of the condition that's our breaking point here. So we're going to call n an m number if p to the p does not divide n for every prime p. So it's sort of a generalization of like square free if you want. We want to insist that p to the p does not divide our integer n. So yeah, every square free number is an m number. 54 is not an m number since 3 cubed divides 54. But you can work out the m numbers have a nice asymptotic density given by this very rapidly converging Euler product. So it's easy to compute lots and lots of digits of this constant if you want. And in this math overflow post that Rechamon made, some other people, Koenig and Alexeyev, piped in, and they conjectured that every m number is matchable. And that's still open, but our main result is that we prove this for almost all m numbers. So in fact, we show that the density of the matchable numbers is exactly this constant that showed up on the previous slide. So there's a little bit of some numbers that aren't m numbers that are matchable. We conjecture that there are no m numbers that are not matchable. But in any case, the density is exactly this density of the m numbers. So as we've got these 2 ingredients. We've got an upper bound where we showed the matchable non-m numbers have density 0, and a corresponding lower bound where the non-matchable m numbers also have density 0. And along the way, we can't prove that every m number is matchable, but we do in fact prove that every square free number is matchable. So that's actually kind of what we'll work through here. And the upper bound is pretty easy. It's basically just that proposition I already showed. So if you've got a non-m number, that means that p to the p has to divide u for some prime p. So our proposition says that, well, if it is matchable, despite being divisible by p to the p, then tau of u is less than p squared. And it's easy to show that such integers are pretty rare. In fact, you can get a nice upper bound for the number of matchable non-m numbers is at most x over log x to the 1 plus little o of 1. And this is essentially best possible, because if you take basically our example of 54, you can show that 27p is always matchable for any prime p that's not 3. And if you count those, you get essentially x over log x. So in some sense, our bound for the number of matchable non-m numbers is close to best possible. All right, so for the lower bound, we're going to work through it for the square free numbers. So if we want to show that every square free number is matchable, we actually split into two different theorems. So first we have a case where we've got lots of prime factors. So we show if every square free number with at least 45 prime factors is matchable. And then we've got a different theorem that proves that every square free number with at most 44 prime factors is matchable. And in some sense, both of them use a lot of the same ingredients. In particular, both of them use Hall's theorem. So Hall's theorem is sort of maybe you can view it as a graph theoretic result, but it's just showing that in a bipartite graph, you've got a perfect matching, which you can think of this coprime matching as an example of a perfect matching in this coprime number graph. It exists if and only if the neighborhood of every set S has cardinality of size at least S for every subset of one side. Okay, so that's basically what we have to show, is that if we take subsets of one side in this matching and we look at the neighborhood in the other side, that cardinality is always bigger than what we started with. Okay, so let's start with the case when we've got lots of prime factors. So suppose we've got some number with at least 45 prime factors. So we first deal with the sort of small prime factors. So they're sort of easy to just break off, and they're sort of predictable. We know how to deal with them. So right U is P1, P2 up to P sub L. So we've got L prime factors. That means that the number of divisors is 2 to the L. And we're going to sort of split off the first J smallest prime factors. So M sub J is going to be the product of the smallest J prime factors, and N is all the remaining large ones. And J is going to be a parameter that we have to pick depending on L. So in order to get down to 45, we had to really get creative with J when U was less than 100, say. When the number of prime factors gets really large, it's optimal to take J to be about the square root of L. But all we need for this talk is just that no matter what L, the number of prime factors is, we can always take J to be at least 3. Okay, so then we've got this lemma that says, so we need to match up the divisors of U with the interval 1 to 2 to the L. And we can partition this interval into a whole bunch of equal-sized sets, A sub V. V is the parameters that are, the V's are our divisors of M sub J. So it's the collection of small prime factors that we have to deal with. So each of these has size tau of n. So tau of n is that rough part. So we're sort of just breaking it up into chunks. And we say every element of this set A sub V is coprime to V. And we also need that A sub V is approximately a whole bunch of arithmetic progressions. So it's not too poorly behaved. So now, if we want to find a coprime matching, to start with, well, we can just find coprime matchings between these sets A sub V and V times the divisors of n. And, well, we've pulled out all the n is coprime to V. So coprime matchings of this sort is the same thing as coprime matchings of this sort. So as long as we can find a whole bunch of coprime matchings that look like this for every V, we can just go and stitch them all together to get a coprime matching for U. All right, so what do we do here? So this is where Hall's theorem shows up. So we're going to take some subset S of A sub V. So fix a V, doesn't matter which one. We pick a subset of that set, and we're looking at the neighborhood of S. So the neighborhood is going to be, since this is a subset of the interval, the neighborhood is going to be a subset of the divisors of n. And in particular, it's going to be all of the numbers that are coprime to everything in this set S. So it's just all of those divisors that are coprime to every element D in this, every element S inside the subset S. That's what the neighborhood of this set S is going to look like. So our goal is to show that this neighborhood is always larger than the set we started with. So our key idea is we're going to take the integer k to be the smallest number of prime factors that any element S shares with n. So look over all the elements of your set and just say which one shares the fewest number of prime factors possible with the number n. So if S achieves this minimum, that means it's coprime to this many prime factors of n. So it's adjacent to a lot of divisors. So in particular, it's adjacent to at least tau of n divided by 2 to the k divisors. So that tells us the neighborhood of S is at least this big. we sort of get a lower bound for how big this neighborhood is. So we just need to find some way to force that S has to be smaller than this bound. So if k equals 0, so if you've got at least one element of your set that doesn't share any prime factors with n, then you immediately win, because that tells you that the neighborhood of S is all the divisors of n. So you sort of get for free that the size of S is at most tau of n, which is the size of the neighborhood of S. So we just need to deal with other values of k. Okay, so this is where we started with before. We've got k is this minimum. Let's let f of n be the sum of the reciprocals of all the divisors of n. So we can show that this f of n is always at most 0.93. So you might wonder, how do we do that? If our number could be divisible by all sorts of primes. Well, we're using the fact that we're splitting off all the small prime factors into our m sub j. So u only contains large prime factors of n. And we've got this parameter j. One of the things that j has to do is we pick it so that this is always true. The sum of the reciprocals of all the large prime factors is always at most 0.93 by the way we pick j. So now if we want to count how many a's in our AV have this property, well, it's at most tau of n times f of n to the k divided by k factorial. You're just exponentiating this reciprocal sum to the k, so you're getting every possible way of dividing by k prime factors in the denominator. You divide out by a k factorial because you get that from sort of the binomial theorem. And then there's some error term that has to do with, well, you've got a whole bunch of arithmetic progressions, if you remember. So there could be a little bit of big O of 1 for every single arithmetic progression. I'm going to mostly sweep that error under the rug. But the error, dealing with the error, is really where we get that lower bound of 45 from in this theorem. So let's just look at the case k greater than 4. So if k is greater than 4, then f of n to the k over k factorial, this term, is at most 0.93 to the k over k factorial. And it's easy to show that this is always smaller than 1 over 2 to the k. So if your set S contained every single element that shared at least k prime factors with the number n, well, then we still get that the size of S is bounded above by this tau of n over 2 to the k, and so it's less than the size of the neighborhood of S. All right, so after k equals 4, things get a little more interesting. So in k equals 3, we don't quite get the argument that we just had on the previous slide, because that bound we had before, f of n cubed divided by 3 factorial, is 0.134. But if we wanted to win, we'd need this to be less than 1/8. And this is too big. It's bigger than 1/8. So how do we fix this? Well, we break into sort of two cases. So first, we suppose we know that since k equals 3, that means there's at least one integer in our set that shares exactly 3 prime factors with n. So let's call that element S1. Now let's first suppose that it's unique in the sense that there isn't any other integer with 3 prime factors that some other element S shares exactly 3 prime factors. So we're saying that every element of S either has GCD equal to precisely this Q1, Q2, Q3, or S shares more than 3 prime factors with n. Well, in this case, we can find an upper bound for the size of the set S. It's, well, the number of things in our interval that are divisible by Q1, Q2, and Q3, plus the bound for the number of things that share at least 4 prime factors, plus our error. And we can get a lower bound for this thing because I said, well, J, we're always going to split off at least our smallest 3 prime factors. So in the worst case, those three prime factors are 2, 3, and 5. So the large prime factors, the smallest they can be are 7, 11, and 13. So if you plug those in, well, now you get a bound that the size of S is at most 0.033. Just plug in 1001 here and work out what this is. So we win by a lot. This is much less than 1/8. So we're good to go here. All right, what happens if it's not unique, the other case? So now we can suppose that, that S contains 2 elements where the GCD of S1 with n is 3 primes and S2 with n is 3 different primes. So in particular, this product is not equal to that product. Well, these two things could still share a lot of prime factors. All we're saying is that there has to be at least one prime here that's not over here. But together, if you take the union of these 3 primes with these 3 primes, you've got to have at least 4 primes showing up. So together they exclude 4 different prime factors of n. So if you look at the neighborhood of S1 intersected with the neighborhood of S2, it can't be too big. So it's at most tau of n divided by 2 to the 4th. So by an inclusion-exclusion argument, that now gives us an improved lower bound for the neighborhood of S. In particular, the neighborhood of S has to be at least the cardinality of the neighborhood of S1 joined with the neighborhood of S2, and we get a nice lower bound of, instead of tau of n over 2 to the cubed, now we've got 3 tau of n over 16. And if you look at 3/16, that's about 0.1875. That bound we got from the sieve was 0.134. So now we win. And we in fact get that the cardinality of S is less than the neighborhood of S in this case as well. All right, we've still got to deal with k equals 1 and 2. I won't talk about them here. They're similar ideas, just increasingly more complicated. We've got to bring out more and more arguments to sort of make it work. All right, so what about theorem B? So this was the other part of the argument. This is the square-free numbers with at most 44 prime factors. So the hard part is sort of a monotonicity argument. So we show that, in fact, we can reduce to the case where U is not any L primes, but in fact, it's the first L odd primes. So as long as you can prove it for sort of the worst case, the case when U consists of the product of the first L odd primes, then you can show it for any integer with L primes. This actually isn't as easy as you might think. Our first draft that we submitted to the journal turned out that our argument didn't work here, and we had to come back. We thought that our argument might have been tanked, but luckily we were able to patch it up. So at this point, we can just sort of proceed by cases, again involving this integer k, but instead of this longer argument we had before, we use exact counts that we went and computed. So we were able to compute out to the interval of 1 up to 2 to the 45, work out exactly how many integers had all these various different counts. So we're sort of able to just get these two things to overlap. We could bring the theorem A down as far as we possibly could, down to 45 by sort of tightening the screws as far as we could go. And then luckily, that was just about where we could get to on the computational side. So we were able to run a computer for a couple days, chewing through, counting exactly how many things had all these prime factors, and it worked out to, luckily, yeah, just work out in terms of getting these two things to overlap. So we can extend this to M numbers, basically by more or less carrying through the same argument. We just have to assume that there aren't any remaining large prime factors that appear to high powers. We deal with the prime factors that look like this in the same way that we work with the small primes. They're sort of, turns out if you've got a divisor that's p to the p minus 1, it's actually pretty easy to handle. And so we get that almost all M numbers are matchable. The non-matchable M numbers form a density 0 set. All right, so to conclude with a couple quick open problems, there's still this main conjecture that is still open. So is every number M number matchable? So we still don't know the answer to that, but one way to do it would be good question. No, I don't. Yeah, could probably work one out. We could sort of yeah, I'd have to think about it for a minute, but they'd have to be pretty large. They'd have to have an awful lot of prime factors. So one way to prove this that we tried for a while that we couldn't quite get it to work, but Koenig made another post on that Math Overflow post. So he observed that if you can prove that any divisor of a matchable number is also matchable, that would imply this result, because it's pretty easy to show that the product of all the p to the p minus 1s is always a matchable number. But yeah, sort of, and as far as we can't find any counterexamples to this, it seems like every divisor of a matchable number is always matchable, but we can't make the argument work. So finally, if you wanted to try to extend our argument to all matchable numbers, all M numbers, so we were able to get all square-free numbers. So you might ask, well, why can't you just extend it to all of the square-free, all of the M numbers? Well, they said the limiting case is sort of these numbers that have lots of very large prime factors to very high powers, but not too high. If it's p to the p minus 1, it's easy to deal with. And if it's really close to p to the p minus 1, it's also pretty easy to deal with. So sort of the worst case, if you wanted to try and say, what's the absolute hardest thing to tackle at this point? It would be numbers that look like this. So if you wanted the smallest counterexample, it'd probably be something that looks like this, where I don't know how large you have to take p before we can't do it anymore. So 2 to the 1 times 3 squared times 5 cubed times p to the ceiling of p over 2. So our argument has no hope of handling these numbers in general. So this is sort of the biggest open problem. So if you wanted to tackle this, try to see if you can have no idea how to do these numbers in general. All right. Thank you. Yeah. Prime number p, and you're just taking the product of all the p to be 101 here. And you take the product of 2 to the 1, 3 squared, 5 cubed, all the way up to 101 to the, what is that, 50? I have no idea how to prove that number is matchable. I think it is. The conjecture is that all of them are. These are all m numbers, and the conjecture is that the p, so you don't know how to handle them.
Other questions for Nathan? Not. Thank you again. The next talk will be in about 5 minutes.
So yeah, love the
Okay.
to come here.
So the first morning's talk